So actually, we are lucky. In the last talk of the session, this is presented by two speakers. Jan Romann and Hugo study computer science at the University of Bremen. And within the student project NAMIP, which stands for Network Access Makes IoT Better, they are dealing with security and interoperability issues of the IoT, where they focus on self-description standards. They implemented support for MUD, which stands for Manufacturer Usage Description, and the Web of Things thing description in RIOT. And if you're both ready, then you have the stage.
Yes, is the audio fine?
Yeah, I can hear you. It's clear and loud.
You can see our screen.
I can see your screen.
Oh, very good. Very good. Yeah. Okay, yeah. Thank you for having us. And hello, everyone. My name is Jan. This is Hugo. And yeah, we are going to talk about self-description standards, as was already mentioned, and yeah, if and how they can improve the interoperability and security of IoT devices, yeah, and how you can use them with RIOT. Yeah, as first some information about us that has already been mentioned in part. Yeah, we are a student computer science project here at the University of Bremen. Yeah, projects like ours are actually a mandatory part of our curriculum. And yeah, in this talk, we are going to present the results from the bachelor phase that we obtained so far. The project is going to be continued as a master's project. And yeah, our goal was to improve yeah, usability and security, and of course also contribute our implementations and findings back to the open source community. Yeah, first we want to discuss what problems self-description standards attempt to solve and why it might be useful to work with them. Yeah, two of the main problems we are dealing with in the IoT today concern security and interoperability, as you might know. This means that on the one hand, devices are often poorly secured and don't use encryption or authentication, for example. They might also simply be untrustworthy and could perform undesired operations behind the user's back. And lastly, manufacturers tend to abandon their devices once they are no longer sold or the warranty has expired, which of course can leave these devices vulnerable to attackers when they no longer receive any updates, for example. On the other hand, many manufacturers have their own ecosystems, which are necessarily compatible with the ecosystems of other manufacturers. Yeah, this is also caused by the fact that manufacturers might rely on closed or proprietary standards, which are unusable by other manufacturers and the general public, which can cause devices to not be able to interact with other devices from other manufacturers, and of course also complicates the use of these devices for the actual users, for the end users. Self-descriptions are intended to provide a solution to both the security and interoperability problem. As part of our project, we've worked with two different open standards, each attempting to solve one of the aforementioned problems. The first one we'd like to talk about is the Web of Things thing description, short WoT, which is specified as a W3C recommendation and mainly aims to improve device interoperability by describing a device's capabilities and exposing them to other devices. The other standards we have worked with is the manufacturer usage description, which aims to improve the security of devices by describing the necessary network access a device needs to actually fulfill its function. This information can then be used to reduce the attack surface of both the device and the network the device operates in by limiting the access from and to the device to what is actually needed by the device to properly function. And this standard is specified in RFC 8520, and therefore an IETF standard. We now want to present both standards and our implementations in more detail. First, we want to talk about the Web of Things, thing description. The Web of Things as a family of standards or specification wants to apply principles from the web to the Internet of Things. At its heart lays the thing description, which serves as an entry point to a thing, which is comparable to the index HTML of a web page. And TDs are serialized as JSON and consumed by other devices that want to interact with the thing that corresponds with the thing description. A consumer implementing the WoT standard and that supports the right protocols or suitable protocols is then able to interact with a thing solely by processing the thing description and triggering the affordances that are described in a thing description. These affordances can be found at the bottom of this slide and are the main part of a thing description. We are able to describe properties, actions, and events in the TD. And we are also able to provide metadata, for example, a title, also a description, and it's also possible to provide security parameters and configurations. As already mentioned, interaction affordances can be properties, actions, events, and properties might be, for example, the status of a smart light or a temperature value that is read by a sensor. Actions might, for example, the possibility to toggle a smart light. And finally, events. You might, an example for an event might be that a sensor informs other devices that have subscribed to a certain event if this event occurs. For example, when a certain temperature level is being reached. TDs expose the capabilities of a thing and offer them to potential consumers. And each interaction affordance contains a forms field for mapping the affordance to protocols and the respective resources that are hosted by the thing. Here we can see an example for such an interaction affordance, property. We have here also properties are not only interaction affordances, but also data schemas, and therefore they provide schema information, like, for example, the data type that is to be expected when retrieving the property and unit, in this case, degrees Celsius. And at the bottom, you can see the forms field, which contains a URL, in this case to example.org/temperature, where you can retrieve the temperature value using the CoAP protocol, which is indicated by the CoAP URL scheme. Another example would be this action, which can be used for setting the state of a smart lamp. You can see that the general structure is similar, but in actions you're also able to specify input and also output data, for example, and different parameters are assumed by default for the protocol bindings. So, for example, actions using a CoAP URL would default to using the post method, while properties would use the get or put method to read and write to properties, or write to access those property values. Lastly, there's also some metadata in this interaction affordance included in this interaction affordance, which could, for example, be used in graphical user interfaces. Yeah, but after describing what a TD looks like, the question also arises how we are able to obtain TDs. There are a number of different ways specified, but in our case, we primarily relied on specified well-known UI, well-known WoT thing description, and also the core link format and the well-known core, well-known UI, which enables us to also access or acquire thing descriptions by the content type application TD plus JSON. All of this enables us to use multicast discovery and do so by using CoApp as a protocol. And to bring the web of things to RIOT, we worked together with Philip Bloom, who initiated the work on a WoT module for RIOT. Philip also spoke about the web of things at last year's summit, so check out his talk as well if you're interested. The current state of the WoT implementation is still work in progress, but it can also already be used to create WoT applications with RIOT. The module makes it possible to serialize the thing description as JSON at runtime, and makes it possible to be retrieved using CoApp, depending on the GCoApp module. And it is also possible to use WoT files as an input for the generation of RIOT application with WoT support, as we have implemented the code generator using Python. To illustrate how both TDs and the discovery mechanism can be used with RIOT, we've set up a weather station, which itself runs on a Raspberry Pi, which is able to automatically find sensor nodes in the local network by retrieving their thing descriptions using multicast discovery and CoApp. The weather station filters the obtained thing descriptions for compatible sensor values, for example, temperature and humidity. And based on the TDs, the weather station is then able to retrieve those sensor readings periodically and display them in the UI. We implemented the logic of the weather station with Node-RED by creating a custom module for Node-RED, which is a graphical editor for implementing applications not only for the IoT, but there are many modules which are designed to be used in the IoT. And our module also makes it easier to create WoT applications, especially for persons that are not so tech savvy. The module utilizes the reference implementation of the Web of Things called a Node WoT for the actual interaction with the things and to retrieve the sensor values. Based on the TDs, the things are displayed in a graphical user interface and listed in a table on the right. And this table is created using the metadata contained in the thing descriptions. And on the left-hand side, you can see that the sensor readings are plotted in as a graph, which is automatically updated. And this example shows that that WoT can simplify machine-to-machine interaction, but can also be used for generating user interfaces automatically.
Next, we'd like to talk about MUT in a little more detail. As we already mentioned in the introduction, The MUT standard is specified by the IETF as RFC 8520. Manufacturer usage descriptions allow a manufacturer to self-declare how a device needs to be able to access the network in order to function properly by specifying, for example, which hosts the device must be able to access. The configuration is represented as a so-called MUT file, which can be written for each device model. These files are JSON files that are instances of the MUT young data model, which basically means they follow a certain schema or are formatted in a certain way. Aside from the typical meta information about the device and the file itself, MUT files mainly consist of access control lists, or short ACLs, that describe allowed and disallowed network traffic from and to the device. An example of such a file can be seen here. As we already said, the MUT file consists of two parts, one for meta information and one for the actual access control lists. The meta information part includes the usual information about the device and the MUT file, like the last time the MUT file was updated, or the device name, etc. Moving on to the access control list part of the file, we can see that each access control list consists of a list of access control entries, or short ACEs or ACEs. An example of such an entry is shown here. This example entry, when used in MUT file, would, for example, specify that traffic coming from test.example.com from port 443 should be allowed as long as the connection was initiated by the device. It should be noted that these entries do not necessarily need to refer to IP addresses, as one might be used to when creating firewall rules, but can instead also refer to DNS names. Additionally, there are also special keywords that can be used there to refer to specific devices or device classes. An example of that would be the same manufacturer device class, referring to all devices made by the same manufacturer as the device the MUT describes. One question that remains, though, is how these MUT files are actually applied to the network. To answer this question, we would like to take a look at the architecture specified in the standard, which describes three main components. First, of course, we have the thing itself. In the MUT standard, the thing's only responsibility is to provide a MUT URL to the network. The probably most prominent way of doing so would be using DHCP, so sending the MUT URL alongside a DHCP request inside of an option. But other ways are specified or could also be specified in the future. This MUT URL is then either directly received or forwarded to the MUT controller. Forwarding would, for example, be necessary when the MUT URL is provided to another network component. In the case of DHCP, for example, this might be the DHCP server inside of the router. And the MUT manager is then responsible for retrieving the actual MUT file from the specified URL and instructing other network components to change their configuration accordingly. The file itself is stored and served to MUT managers using a MUT file server, which is just a server provided by the manufacturer serving these files using HTTPS. Because the files are stored on the server and not on the things themselves, they can actually be changed without having to update the device. This is one of the advantages of this approach. It can be useful, for example, to restrict access to devices with known security vulnerabilities or running old versions of some software, or which can no longer be updated at all. To facilitate this, MUT files have an expiry time after which MUT managers need to re-request them. Yes. Before we talk about what additions we made to RIOT to allow for MUT support, we first want to talk about the other parts of the MUT specification we implemented as part of our project. We found that previously existing MUT manager implementations were either no longer maintained or not suitable for our use case. In our case, we were focusing especially on home networks. Our implementation of a MUT manager consists of a controller component performing the actual role of the MUT manager according to the specification by managing MUT files and devices, as well as an additional enforcer component which can run on Linux-based routers and then translates the instructions the controller gives the enforcer into actual firewall rules. The controller also allows for customizing rules and viewing devices using a web front end. As shown here, these are some screenshots from the web front end. Oops, skipped the slide. Yes, both controller and enforcer are designed to run on lower-end devices like Raspberry Pis. For the controller, we provide a Debian package that can be installed on Raspberry Pis running Raspberry Pi OS. The enforcer was specifically written with open WRT routers in mind, and therefore we also provide open WRT packages for installation using OPKG. To make it easy for users to actually use the software in home networks. One question that remains is how we can deal with devices that do not support MUT, since adoption of these rather new standards is, of course, pretty low. For that purpose, we actually wrote another component called the legacy service that can work together with the controller and enforcer to analyze the network traffic of devices that do not support MUT. This is primarily done by inspecting the DNS requests the device made to the local DNS server and comparing it to a repository of MUT files. MUTs that match the device behavior can then be recommended to the users and used instead of manufacturer-provided ones. The aforementioned repository is crowdsourced, so everyone who wishes to add support for another device can do so by submitting a contribution there.
Yeah, when it comes to RIOT, it is already possible to include MUT support in your applications. For enabling this feature, we added the respective MUT option to the DHCP client or DHCP 6 client, and a pseudo module for indicating whether the option should be included in the client's DHCP messages. We also added the possibility to request non-temporary addresses, which was necessary because the DHCP client so far only supported prefix delegation, and because our controller can so far only work with address leases. However, we have already opened a PR for stateless DHCP v6 as well to also be able to use MUT in addition to stateless address auto configuration in the future. The MUT URL can either be configured in the makefile of the application or using kconfig. So what did we learn doing all of this? When it comes to WoT, we saw that both the discovery of things and the use of TDs to perform interactions works quite well already. However, one weakness of the specification is that there's no support for composition yet. So this means that you cannot express that a thing consists of multiple components, for example, multiple sensors, which reduces the expressiveness of TDs and makes it more difficult to reuse definitions with conflicting affordance names. Last but not least, text-based format like JSON is not ideal for the use with constrained devices, and therefore it should be possible to also serialize TDs in binary formats like CBOR, for example, in the future.
When it comes to MUT, we have identified 3 main issues we had while implementing the standard. First, we found that DHCP is not necessarily the ideal standard for emitting MUT URLs, especially when we are talking about IPv6 networks, where stateless address auto-configuration makes requesting an IP address from the DHCP server unnecessary, so it is no longer trivial to send the MUT URL alongside such a request. Possible alternatives, aside from, of course, using stateless DHCP v6, as already mentioned, could be using core resource directories to refer to the MUT files there. Second, we also found that the advantage of MUT files that they can also refer to DNS names and not only IP addresses is difficult to implement in practice. Because the actual firewall needs to work with IP addresses and cannot work with DNS names, at some point these names must be resolved. This is difficult when dealing, for example, with DNS load balancers or other mechanisms which cause DNS entries to change frequently and which would make efficient caching difficult. Things may not even necessarily get the same IP addresses for one entry when resolving domains themselves, even when this resolution happens at the same time because of this, especially when they are hard-coded or configured to use a different DNS server from the one that is running locally. Lastly, it is also not easy to properly isolate devices inside of the network, especially when talking about home networks. Virtual LANs or VLANs might be a solution for that, but using them today requires enterprise-grade hardware, which is usually not found in home networks. Probably solving this problem might require adding VLAN support to consumer hardware or developing different methods for device isolation.
To conclude, both MUT and WoT are very promising standards, which actually can contribute to making the IoT more secure and also improve the interoperability of IoT devices. However, there are some weaknesses both in the specifications and our implementations, especially with regard to constrained devices. So there's still a lot to be done, and it would be awesome if you could join us in working with these specifications and trying to improve them. You can find almost all of our implementations in an organization on GitHub that we have set up. And yeah, we are looking forward to your feedback and contributions. And we are thanking you for your time. And yeah, we are open for any questions you might have.
All right. Thanks, Hugo and Jan. It was a very informative and illuminating talk, at least for me. I think the first time I heard about MUT was a couple of weeks ago, and it's interesting to encounter it here again. So do we have a couple, maybe 1 or 2 questions from the audience? I mean, we are very short on time, but maybe there are some. Doesn't look like it. Actually, I have one very brief question. I mean, you were talking about WoT, and it's a descriptive language. I mean, it's the things description, so I can imagine it can get quite descriptive. Do you know if, I mean, it probably depends on the use case, but if you like request a TD, how large can a packet be? I mean, can you make some estimations on, does it fit into a 15.4 packet, for example? Would you need to fragment it?
Yeah, this is actually an issue with CoAP. So to transfer the TD to a consumer, we are utilizing a blockwise transfer. So the TD is sliced into multiple packets, or each with a fraction of the total payload. So yeah, this is actually an issue, and I think in context like 6LoWPAN, this issue becomes even more severe. So using CoAP, not CoAP, but CBOR for serialization is almost unavoidable to actually be able to use a WoT in these contexts.
Mm-hmm.
But there's also an activity to define a number of profiles, which could define a defined set of affordances, for example, so that you might be able to save some bandwidth and do not need a TD that is too verbose.
Okay, so as a form of stateful compression or something like this. Yeah, great. I think that's it. I mean, there are no other questions in the chat. So we're at the end of our session. Thanks again, Jan and Hugo. And yeah, there's also like a notice in the chat now from Matthias. So in order to align again with the initial schedule, we will shorten the next break from 30 minutes to 50 minutes. So we will see you again at 3:15 UTC 0. All right.